Hello, everyone. This is part 2 in our bias in epidemiologic studies. So in part 1, we've talked about DUGs. In this one, we're going to talk about confounding. So part 1 was overview and how we can use directed acyclic graphs in addressing epidemiologic questions. In some ways, this is related also with addressing confounding. Then we'll talk about the other two types of bias that we have in epidemiologic studies, which is selection bias and information bias. So our learning objectives in this part is trying to understand what confounding is, the epidemiologic definition, how it leads to study bias. We'll try to talk a little bit in how we can use the DAG structure and the causal inference thinking to address confounding. We'll learn about methods to control confounding in both the design stage as well as the analytic stage. We'll also talk about how we can assess confounding from data and try to finalize by talking about some of the common confounders that we have in epidemiologic studies, particularly in genetic epidemiologic studies as you think about your projects in the future. So let's take this simple example where a newspaper, a Ugandan newspaper, Daily Monitor, reported that prayer lowers blood pressure. So the newsletter said, attending religious services lowers blood pressure more than tuning into religious TV or radio. A new study says, people who attended religious services once a week and prayed or studied the Bible were once a day were 40% less likely to have high blood pressure than those who didn't go to church every week and prayed and studied the Bible less. So based on the information that is provided, one could come up with 3 conceptual models. So the first model is maybe those individuals who go to church and who also prayed have lower blood pressure. So in this case, as we have seen from our causal diagrams from DUGs in the prior session, that this would be a causal relationship. So we can say that prayer causes lower blood pressure. But we have 2 alternative explanations. Maybe those who are healthy are more likely to go to church and more likely to pray, and hence they have a lower blood pressure. So the relationship between going to church and praying and having a low blood pressure is not causal. It is a correlation. So in this case, it wouldn't be a causal relationship. We could think of a third scenario where individuals who are more likely to be social are more likely to go to church and interact with others, and they're more likely to pray. In that case, because they have less stress, they would have lower blood pressure. So in the same way, like the second case, we would say prayer doesn't cause lower blood pressure, or the 2 are correlated. So it's not a causal relationship. So from the information that is provided to us from this simple example, we can't tell which one is correct. And this is the idea behind this is what we will discuss about, which is the idea of confounding. So from the examples in the previous one, we saw that there is a common pattern of a third variable mixing the effect, which we call it confounding. I'll define confounding in a minute. The goal of the main idea behind confounding is it distorts the estimated effect due to common cause or unblocked backdoor paths. So it's a mixing of effects. In this case, we are on purposely not having an arrow between our exposure and an outcome, because we are assuming no causal effect of A on Y, or what we call it under a null hypothesis assumption. But for the purposes of our interpretation, we'll think about A is the exposure and Y is an outcome, and not having an arrow between the 2. So what is the formal definition of confounding? So a confounder from epidemiology point of view is a risk factor that is unevenly distributed between the groups to be compared. And this is really important. Oftentimes, people try to define confounder based on statistical analysis, which is wrong. So I want you to really understand the concept behind an epidemiologic definition of a confounder. So more formally, for a variable to be a confounder, we would define it in this way. It needs to fulfill 3 criteria. The first one is the confounder needs to be associated with the exposure in the source population. A confounder needs to be a risk factor for the outcome independent of the exposure. And a confounder should not be in the causal pathway between the exposure and the outcome. Or it shouldn't be the consequence of the outcome. So it shouldn't be in the downstream of the outcome. So it shouldn't occur after the exposure. And we'll discuss this using several examples. So let's take the following examples, trying to see the 3 criteria. The first one, we have an exposure, which is age, an outcome, cervical cancer, and a potential confounder, prior HPV infection. So we have an exposure, age, and a potential risk factor associated with the outcome. So the confounder is associated with the outcome, but it's not associated with the exposure. So it's a risk factor for the outcome, the second criteria, independent of the exposure. It is also not in the causal pathway. So it's not between A and Y, it's not in between. So it's not in the causal pathway, so it fulfills the second criteria. However, it doesn't fulfill the first criteria because it's not related with our exposure. So this wouldn't fulfill the criteria for confounding. Let's look at the second example. So in the second example, we have the exposure, which is blood pressure. The outcome is cervical cancer. The potential confounder is salt intake. So we can see from this causal diagram that the first criteria is made because the potential confounder, salt intake, is associated with the exposure. It is also not in the causal pathway, or it's not in between A and Y. So it meets the third criteria. However, the second criteria is not met because the potential confounder is not a risk factor for the outcome. It's not a risk factor for the outcome. So it doesn't fulfill the criteria for confounding. Let's look at the last example. The last example, we have a genetic haplotype, which is the exposure. The outcome is cervical cancer, and the confounder is oxidative stress. So you can see that the exposure and the confounder are associated. The exposure and the outcome, they have in between the confounder, which is it's in the causal pathway between the exposure and the outcome. So this violates the criteria that which is criteria 3. So the exposure is associated with the outcome, it's associated with the exposure. However, it lies in the causal pathway between the exposure and the outcome. So as you think about a confounder, thinking about the 3 criteria is really important. Even if you have an exposure that is associated, a variable that is associated with the exposure, a variable that is associated with the outcome, it shouldn't be in the causal pathway. It shouldn't be between the exposure and the outcome. It shouldn't be the consequence of the exposure. So in this case, C is the consequence of A, or oxidative stress could result because of this specific genetic haplotype. Let's look at some more examples, because you might ask, why should we care? So if we take the classic example, epidemiologic example of smoking and lung cancer, and if we design a study and select all smokers in a high school between the ages of 15 and 20, and all non-smokers in a geriatric unit between the ages of 75 and 90, we could find that smoking is good for health, since smokers experience less disease than non-smokers. So the consequence of that in this case would be the relationship between smoking and disease is confounded by age, because age is related with smoking, so it's related with the exposure. It is also related with the outcome. It's not in between, it's not in the causal pathway between our exposure of interest and our outcome of interest. Hence, it satisfies the criteria for confounding. And the two groups are not comparable with regards to this crucial or third variable. So the consequence of this would be one would implement a prevention or an intervention program without addressing the other risk factors. And then the impact might be much more smaller than expected. So there is a real impact in designing an intervention or in implications involved in clinical decision making if we don't take confounders into account in our epidemiologic studies. Let's look at another example. This is also another common example that's used in infectious disease epidemiology. So if we look at the study that was done in Tanzania, trying to assess the impact of owning a mosquito net, ITNs, on malaria diseases, comparing those who own mosquito nets and those who do not own, we could find a great benefit of owning a mosquito net, owning a treated mosquito net. If people who own a net are also richer and have therefore better housing, better socioeconomic status, better hygiene, better nutrition, then one may overestimate the impact of owning a mosquito net. This is also another example of confounding. So if we can look at, if we take socioeconomic status, which is associated with our exposure of interest, owning a net, it's also associated with our outcome of interest by way of having a better housing, better hygiene, and better nutrition. We can say that this is a confounded association. What would be the consequence of this? Well, the consequence is if one would then implement a program that provides mosquito nets without addressing the other risk factors, the other underlying socioeconomic risk factors, then the impact might be much more smaller than expected. So the good news is, unlike the selection bias and information bias, there are ways to control confounding both in the design stage and in the analysis stage. We will not be able to control selection bias and information bias at the analysis stage. This is something that we'll discuss in the next session. But for confounding, there are ways that we could minimize confounding at the design stage as well as at the analysis stage. We'll look at them one by one. But in the design stage, we could use either randomization or matching or restriction. In the analysis stage, we have various tools, including stratified analysis and pooling, multivariate modeling or regression, multivariate regression modeling. We could have inverse probability weighting. So those are analytic tools that one may take into consideration in minimizing or addressing confounding. So let's look at randomization as a design stage. So this is something that we talked about in our study design when we talked about randomized controlled trials. So as you remember, randomization of exposure or treatment can break the association between all potential confounders or variables in the exposure. So in a way, it balances the distribution of the covariates. I mentioned this in the RCT, where if you want to know that a study is well done study, or if you want to know if the randomization was done appropriately, you should look at table 1 of a randomized controlled trials in order to see the distribution of key variables that are included in table 1. You should be able to see a balanced distribution. There should be no systematic difference between the distribution of the variables included in table 1. So this is why RCT is the least susceptible to confounding bias, and thus we consider RCT as the gold standard for establishing causality. So if we can think of confounder, and then we have our exposure and our outcome, in a way, what randomization is doing is it's breaking this path by balancing the distribution of potential confounders between the exposed and unexposed, or those with treatment and no treatment. You would be able to balance the factors that might confound or that might mix the association between your exposure of interest and outcome. Obviously, there are many limitations into doing randomization, as we've discussed in the study design lecture, including they're expensive, they're maybe unethical. Sometimes we may not be able to randomize on some things. For example, if we take the one with mosquito-treated nets, we may not be able to randomize households whether they should own or not. And sometimes it's not really feasible, so we may only have access to observational data. But this is one of the best tools that we have in the design stage. The second tool that we use in the design stage is matching. This is often used in cohort studies. We think about in cohort studies, the exposed group could be matched to the unexposed group on some key and potential confounding variables. This prevents an association between the exposure and the matching confounder. So the same way that we have seen. So we have the exposure, we have the outcome, this is the potential confounder. If it's matched, it would be balanced. So matching in case control studies is a little bit complicated, but we can do individual matching or frequency matching in cohort studies. So for example, matching could be done by date of birth, that would be individual matching. Or we could do frequency matching where we're trying to get similar distribution of key variables, for example, age groups within 5 years of difference. So we could have individual matching or frequency matching. As I mentioned, matching in case control studies could be a little bit complicated than cohort studies, but controls could be matched to cases on potential confounders. One caveat though, if you do matching in case control studies, one needs to take into account for matching in analysis to have valid estimates. So let's look at an example. This is an example of a pairwise matching in case control study. In this study, the investigators were interested in looking at if coffee drinking is a predictor of myocardial infarction. The investigators decided each case, in this case, patients with myocardial infarction, could be matched with one or more controls that smoked roughly the same amount as cases. So they're matching them by smoking, because we know that smoking is an important variable, a potential confounder that is associated with our exposure of interest, coffee drinking, that is associated with our outcome of interest, So by matching, the investigators are eliminating how smoking may affect the exposure outcome relationship in this case. The third type of design stage control that we can apply is restriction. Restriction requires all members of your study population to have the same status on a key potential confounding variable. So you might remember, this is something that we discussed in dogs. This would be conditioning. So remember, conditioning on confounders breaks the backdoor path. So it breaks the backdoor path. So this is most useful when the most potential subjects have the same status on potential confounders. So you can't necessarily apply it to everything. For example, this is a study of diet during early pregnancy and development of GDM, or gestational diabetes. The investigators say that they studied 1,733 women with singleton pregnancies enrolled in this study. So by focusing or by restricting their study to singleton pregnancies, they are using this tool as a way to prevent confounding. So this is something that one can do during a design stage. However, there are limitations to doing restriction. If you restrict, it reduces sample size. Your ability to include as many individuals who fulfill your criteria might be limited. It also reduces generalizability. This is something that we talked about at the beginning of part 1, which is external validity or generalizability would be limited. It also eliminates the ability to assess effect modification. This is something that we will discuss in module 4. And sometimes it may be difficult or not feasible or even expensive trying to identify individuals who fulfill certain criteria by applying restriction. So the next stage that we try to do to address confounding is in the analysis stage. In the analysis stage, we have different tools. The first one is pooling. Pooling provides unconfounded estimates of the effect across different strata of the confounder. So we're trying to provide the association between the exposure and the outcome according to different strata of the confounder. So this is conditioning. Essentially, we're doing conditioning. Pooling combines the stratum-specific measures across strata, averaging them to create an adjusted estimate. And we'll talk about this in an example, and it will become clearer. So we try to come up with weights that are assigned information based on different weights. And we have different tools that we use to assign weights. One of the most common tools that we use is a Mantel-Hansel method, named after Mantel and Hansel, for coming up with assigning weights. And there is also an inverse variance weighting, which we're not going to talk about in this case. We'll just briefly touch Mantel-Hansel weighting when we take an example. So what pooling is doing is it's assuming homogeneity, where the effect being estimated is constant or uniform across strata of the confounders. The limitation with pooling is it can become complex if we have multiple confounders. So for example, if you have a confounder that has 5 labels or 5 groups, you would have to stratify the analysis across those 5 different strata. So it will need to categorize continuous variables into something that is manageable or something that is grouped, and it may result in residual confounding. The second type of analysis stage that we use is multivariate modeling. This is something that we'll talk in biostatistics and in our course. Well, you would use a multivariate regression analysis. This is the easiest, but understanding the rationale or the approach behind why we do this is important. The way you do this, you include the potential confounder as a covariate in your regression model. So you would have the outcome Y, for example, and you would have the intercept, and you would have the beta, or the estimate for your coefficient, and then you would have the X variable. This could be, in this case, let's say A, because we're using A as an exposure. And then you could have the confounder, which could be, let's say this beta 1, it would be beta 2, the confounder. So we're doing nothing but taking the mathematical equation of a regression model and adding the confounder as a covariate in our regression model. If we look at this from a causal inference point of view, the model gives the estimate of the exposure effect conditioning on the adjusted confounder or multiple confounders if we have many confounders. This is useful for continuous confounders because we can't use the pooling the same way that we have done it for the Mantel-Hansel estimates, and if we have multiple confounders. Another tool that we use in the analysis stage is inverse probability weighting. Inverse probability weighting removes confounding by creating an artificial or a pseudo population in which the exposure is not associated with the confounder. So we are essentially trying to balance the distribution where the confounder is not associated with the exposure. So subjects are weighted by the probability of being exposed given their values or confounders. We're doing nothing but trying to balance the distribution of the potential confounder. This is particularly useful. It's beyond the goals of this introductory section, but for time varying confounders. So we may have some confounders that change over time. We call them time varying confounders. But what if we have just data, that we are not designing a study and we just have data? Is there a way to evaluate confounding from existing data? So I'll go through simple steps and walk you through an example, trying to show you the intuition behind using this procedure. And it would become easier as you practice more and look at studies that report crude estimates or unadjusted estimates and the ones that take confounders into account. The basic steps that we try to take is, the first one is there needs to be strong association between the exposure and the confounder and between the disease and the confounder. So this is similar to the criteria that we have used earlier for our definition of confounders. And you might ask, what does it mean strong? There may be some degree of subjectivity in that. The next one is the crude and the stratum specific effects must be different. So the crude is the unadjusted and the stratum specific effects should be different. The crude and the adjusted effect measures should be different. This is the crude and the adjusted. Finally, it shouldn't be based on statistical significance testing. This is a ubiquitous problem that I see oftentimes in reviewing manuscripts or in seeing published literature. We do not assess confounding based on statistical significance. So let's look at an example. This would be also allow us to use the idea of pooling. So we'll try to put those two together, show you how to assess confounding from data, but also apply the concepts of pooling for coming up with adjusting for confounders. So let's take this example. The question of interest is, does coffee drinking increase the risk of MI or myocardial infarction? And we're using a case control study where we have 150 cases and randomly selected equal number controls. We'll say that 90 of the cases routinely consumed one or more cups of coffee daily in the year before diagnosis, and 60 of the controls consumed coffee in the same year. So we can put those numbers in our 2-by-2 table. So we have individuals with MI and individuals without MI. 90 consumed coffee and 60 of the controls routinely consumed coffee. And we can subtract from 150 to get the remaining numbers and fill the remaining cells. So we can calculate the odds ratio or the magnitude of the association, because it's a case control study, to calculate the relationship between MI and coffee drinking. So we can take the products of the diagonal cells. So 90 by 90 divided by 60 times 60, which gives us 2.25. So we have established a strong relationship or association between the exposure and the confounder, and between the disease and the confounder. So let's look at this. If we think about this from our causal diagram, what we are saying is, if coffee is associated with MI, it should be a causal relationship. But if it's confounded, or the association that we are seeing is because of smoking, then it would be a confounded association. Our goal is to make sure that smoking is not confounding the association. If it is, we try to adjust or control for it in the analysis stage. So let's try to look at this and break down into the stratum of confounders. So as we mentioned, smoking is our potential confounder. As a reminder, our exposure is coffee consumption. Our outcome is MI. We have the non-exposed group. We have the non-diseased group. And we have this 2-by-2 table, which we have seen in the earlier slides. We could put those into two different tables. Among smokers, we can say that 80 of the coffee consumers were also smokers. So if we take 80, and then the rest would be 10, because we had 90 who are coffee drinkers. So it would be 10 here. 20 of non-coffee drinkers were also in the MI group. We can see that 60 minus 20 would be 40. So we can fill the tables to have the smokers and non-smokers grouped by coffee consumption and non-coffee consumption. So the next question that we want to ask is smoking, is the potential confounder associated with coffee in the source population? This is nothing but our first criteria to evaluating confounding. So the cleanest way to do this is to look at the association among the non-diseased group. So in the non-diseased group, in the non-MI group, what is the relationship between your confounder, smoking, and the exposure? So in the non-diseased group, in the no MI group, so I'm taking those numbers and plugging them here. And I'm taking those numbers and putting them here. We would do the same odds ratio calculation, taking the cross products of the diagonal cells, 40 times 80, divided by 10 times 20. We get 16. So people who drink coffee are 16 times as likely to smoke. So we have established a relationship between our confounder and coffee consumption. So the next question is smoking associated with MI independent of coffee consumption? So here we're focusing among non-coffee drinkers. So the cleanest way to look at it is in the non-exposed group. Remember, our exposure is coffee consumption. So if we focus in the non-coffee drinkers and take those numbers and put them here, we would get this 2x2 table. And we can calculate the odds ratio multiplying the cross products of the diagonal cells. 20 times 80 divided by 10 times 40, we get 4. So we can see that smoking is associated with MI risk. Those who smoke are 4 times as likely to have MI compared to those who are not smoking. And we established this relationship among non-coffee drinkers. So the next step is to look at the stratum specific odds ratios. So those are nothing but what we have seen earlier. So those are the same, the stratum specific cells. So in the stratum specific cells, we can take the cross products and calculate the odds ratio. If we take among smokers, the relationship between coffee and MI is 1.0. Among non-smokers, the relationship between coffee and MI is 1.0. We want to look at, does the crude and the stratum specific effect measures differ? So the crude was what we calculated at the beginning. Among coffee drinkers and non-coffee drinkers, we took the cross products of the diagonal cells and we got 2.25. So the question is, do the crude and the stratum specific effects differ? Yes, they are different. 2.25 is different from 1.0, different from 1.0. So we have strong evidence that smoking is a confounder. We have seen, based on the calculations that we have made, that smoking is a potential confounder. So now we can use the idea of pooling to try to calculate an adjusted estimate. I know this may be too much information, but what we are essentially trying to do in pooling or in applying a Mantel-Hansel adjusted odds ratio is nothing but taking the products of the diagonal cells from our stratum specific effects and dividing them by the total number that we have. So I would be multiplying 80 by 10 divided by 150. And I add that to 10 times 80 over 150 because I have 150, the total number. And I divide that by 20 times 40 over 150, 40 times 20 over 150, and I get 1.0. I don't want you to worry about memorizing this formula. This is just trying to give you an idea how we can take weights from the individual stratum specific values to come up with this way of calculating an adjusted estimate. So as we've said in the prior slide, that the crude odds ratio was 2.25. So this crude odds ratio is different from the adjusted odds ratio from 1.0. So we can see that the crude odds ratio is different from the effect measure. So the pooling combined the stratum-specific measure associations across the strata, averaging them to create an adjusted estimate. So the weights are assigned based on the information that we have. So we've satisfied all the criteria. Strong association between the exposure, coffee consumption, and the confounder, which is smoking. We also established a strong relationship between the confounder, smoking, and MI. We also have seen that the crude and the stratum-specific effects are different. Finally, we have seen that the crude and the adjusted effect measures are different. On the basis of this, we can say that smoking is a confounder in the relationship between coffee consumption and MI. Lastly, let's look at those simple examples, trying to illustrate the point. We're not necessarily going to go over calculating each and individual points, but if you were provided with the data, for example, in the first study, you have a crude estimate of 6.0 and a stratum specific estimate risk ratio of 3.30. The second stratum is 3.5 and the adjusted is 3.3. So based on the values that are provided here, we can see that the crude is different from the stratum specific estimates. The crude is different also from the adjusted estimate. On the basis of this, we can say that the variable that is being evaluated here is a confounder. We can take the next example. We had a crude relative risk of 2.0. The stratum specific is 1.2, 1.02, and 1.1, but the adjusted is 1.08. Similar to study one, we can say that the variable is a confounder because it's different from the stratum specific as well as from the adjusted. Let's look at the third example where we have a crude estimate of 1.1. The stratum specific is 2.0 in both, and the adjusted is 2.0. They are different. Even though the direction is going upwards, we still say that there is confounding. Let's look at the last two. We can see that the numbers more or less look similar. The crude estimate is 0.56. The stratum specific is 0.5. The second one is 0.6, and the adjusted is nearly identical to the crude estimate. On the basis of information provided here, we can say that this is probably not a confounder. Lastly, the example that we have here is the crude estimate is 4.2 and the adjusted is 4.04, and the stratum specific are in between 4.0 and 4.1, and we can say that there's no confounder in this case. This is just to give you an idea. You shouldn't take this as a guideline. You still have to make the distinction and making sure that the criteria for confounding is fulfilled, which includes it has to make biologically sense, and it has to be associated with the exposure of interest, with the outcome of interest, and it shouldn't be in the causal pathway. You shouldn't base it on statistical significance, but this is to give you an additional idea how you can use effect measures to gauge whether a variable is a potential confounder or not. So as shown in the prior example, that sometimes the direction of the confounder could be different. So we could have an upward bias where the relationship between the confounder and the exposure and the confounder and the outcome could be positive, or it could be negative, we say this an upward bias where our observed association might be greater than the true magnitude of association. And sometimes we may have a downward bias where the observed association might be smaller than the true effect, which in this case, the confounder could be positively associated with our exposure and negatively associated with our outcome, or the confounder could be negatively associated with our exposure and positively associated with our outcome. So let's look at this simple example. In the coffee and MI case, we have seen that we have an odds ratio of 16 between coffee and smoking, and between smoking and MI, the odds ratio was 4.0. So based on information that we were provided here, the direction would be it's positive, positive, so we would call it an upward bias, because the crude odds ratio was 2.25, and as you have seen from the adjusted one, the adjusted estimate was 1.0. So you could have a direction of an upward bias or a downward bias. What are some of the confounders that we can consider in epidemiologic studies, and particularly in psychiatric epidemiology? We have seen some of those examples. It could be lifestyle factors that could potentially influence behavioral exposures that we are trying to study. So one of the first things that we try to see is if there are lifestyle factors. The other is social factors, particularly SES is an important social factor that we need to consider when designing psychiatric epidemiology study, for that matter, any epidemiologic study. The other common type of confounder that we see in clinical settings and oftentimes in psychiatric epidemiology is what is called confounding by indication. So confounding by indication is a special type of confounding that can occur in pharmacoepidemiologic studies where we're trying to study the effects of or the side effects of drugs. This type of confounding occurs if individuals who are prescribed a medication or who take a given medication are inherently different from those who do not take the drug. Because they are taking the drug for a specific reason, in medical terminology, such individuals have an indication for use of the drug. That's why we use the word confounding by indication. So the reason for initiating a treatment or taking a drug might be introducing confounding. We can, for example, we can look at the relationship between antidepressant use and autism. So, for example, it could be the intake of selective serotonin reuptake inhibitors, SSRI, and their relationship with autism. Because maternal depression is risk factor or something that might be a reason for taking the SSRIs, and because maternal depression also might have an ideologic relationship with autism, this could introduce confounding, and we would call this confounding by indication. There are other types of confounders that are oftentimes seen in epidemiologic literature. We're not going to exhaustively look at them. I'm going just to talk about a handful of those. The first one is the health status, which in epidemiologic studies of occupational related exposures, we call it a healthy worker bias. A healthy worker bias is also a type of selection bias that we will discuss in the next session, where you would see a relatively lower morbidity and mortality from all causes because people are working, because they are working, they may have a better health status, and hence that might create a healthy worker bias. Another one that has been described in psychiatric epidemiology literature is the healthy warrior effect, which has been seen among deployed military members where good health is a prerequisite for deployment, because there is a selective screening and involved during a training and during selection, that might in a way affect mental health, and hence because of that, deployment might be related with lesser psychiatric conditions. In this study that was published in 2008, the investigators reported that all psychiatric conditions except for PTSD occurred at a lower rate in combat deployed personnel than in those who were not deployed to combat zone. So this is a type of bias that you oftentimes see in those type of studies. The other one is environmental factors. Depending on the geographic location, there may be some environmental factors that are associated with the exposure of interest. So for example, we can take those who live in urban areas are more likely to have exposure to air pollution and may have an increased risk for depression. And because living in urban areas is also associated with stress, that could lead into depression. For that matter, we can look at other outcomes. For example, this could be preeclampsia, where air pollution has been associated with increased risk of preeclampsia, and stress is a risk factor for preeclampsia. The fact that living in an urban area also increases for having higher air pollution, the relationship that you see between stress and preeclampsia could be affected by living condition. So if you have study participants included from urban as well as rural areas, one way to mitigate this is to take that into account either in the design stage or in the analysis stage. Another type of confounder that is often discussed is by genetic ancestry or confounding by population stratification. Because of disease risk may vary between two ethnic groups based on their genetic ancestry, they may have specific type of genes that are associated with an outcome, then that variation might be related with the disease, and hence could create a type of confounding that is often seen in genetic epidemiologic studies. This is an example that was published in 2005 in Nature Genetics, trying to look at the association between a specific type of gene related with lactase persistence and height in a sample of European Americans. So this study looked at frequency of T allele, which is higher as depicted in this graph for people from Northwestern Europe compared to people from Southeastern Europe. So you can see that it is lower in those from Southern Eastern Europe, but it is higher in those from Northwestern Europe. This is a specific gene, and they looked at height is also associated with this specific T allele in this sample. However, this association was not found in other studies. This is a type of classic bias that we see in psychiatric genetics epidemiologic studies, or in general in genetic epi studies. It's called population stratification, something that you will learn more when we discuss population stratification and polygenic risk scores in our genetics classes in subsequent lectures.